An AI can write you a sonnet. It can debug your code. It can explain quantum physics in the voice of a pirate. Now ask it to count the letters in a word. There's a decent chance it gets that wrong. Not because it's dumb, because of something much stranger. This machine has read more text than any human who ever lived, and it has never seen a letter. This is Owlspect. Chapter 1 of How a Machine Learns to Talk. One season, one machine, opened piece by piece. Today, the front door. What does an AI actually read? Here's the reasonable assumption. Computers store text as characters. Your keyboard sends letters. So surely the AI receives letters too. It seems obvious. It's wrong. A few years ago, the internet found a famous example. How many times does the letter R appear in strawberry? Easy. 3. A child can count them. The best AI models on Earth kept saying 2. People posted screenshots. It became a meme. You're probably tired of this example. Here's the thing. The machine is tired of it too. Ask today, and most big models get it right. The question got famous, and today's models have learned this one. But the reason it happened is still in there. Memorized answers hide the seams without removing them. And it still bites. On words nobody memes about. So if a machine that has read the whole internet can't reliably see letters, what is it looking at? Before your words reach the model, they pass through a machine called a tokenizer. It chops text into chunks. The chunks are called tokens. Strawberry doesn't arrive as 10 letters. It arrives as 3 pieces: S, T, raw, berry. And even that is generous. To the model, each chunk is just a number, an ID in a giant list. Strawberry is the sequence 302, 1618, 19,772. No meaning attached yet, just positions in a list. 302 doesn't mean anything. It isn't smaller than 1618 in any way that matters. They're just seats in a very long theater. That list is the model's entire world of text, a fixed menu. About 200,000 chunks for one popular tokenizer. Long words, short words, bits of code, single letters. Every email it reads, every poem it writes, assembled from this menu and nothing else. And there's no side door for new words. 200,000 chunks sounds like a lot. Against every word in every language, it's a pocket dictionary. If a word isn't on the menu, it still gets through, but only as fragments. Onomatopoeia arrives in 5 broken pieces. Now look where the R's went. 1 is sealed inside raw. 2 more are sealed inside berry. The model can see the blocks. It cannot see inside them. It's like showing you a Chinese character and asking how many strokes it took to write. You can see the symbol. Unless you read Chinese, you can't see inside it. And notice, you could still answer plenty of questions about that character, like what it means or where you've seen it. You just can't count its strokes. Neither can the model. So the model does the only thing it ever does. It predicts a plausible answer, and berry is a block the model links with double R. That link may nudge the guess toward 2. You might wonder about the newer, slower models, the ones that show their thinking. They usually get this right, not because they see letters. They learn to work around, spell the word out first, 1 letter per token. Single letters are on the menu too, then count. The blocks are still there, they just route around them. But hold on, who decided the knife falls exactly there? Why ST, then raw, then berry? Who chose the chunks? Here's the strange part, nobody did. The menu isn't designed, it's grown. Before training, the builders run a simple procedure. Start with single characters. Find the pair that appears together most often, in a mountain of real text, web pages, books, code. Nobody consults a grammar book, and no linguist gets a vote. The procedure just counts. Glue that pair into 1 new chunk, then repeat, hundreds of thousands of times. Watch what frequency does. TH fuses early, the most common letter pair in English. IN fuses, then INGER fuses. Run it long enough and whole syllables crystallize, then entire words. Common words are in single, solid blocks. Rare words never do. They stay in fragments. The dictionary isn't written, it's worn in, like a footpath across a field. That's why strawberry splits the way it does. ST is common, raw is common, Berry is common. Strawberry, standing on its own, just missed the cut, so it splits into the pieces that did. And the seams are stranger than they look. Put a space in front, the way the word usually appears, mid-sentence, and it becomes one single block. Same word, different seams. The dictionary doesn't care what a word is, only how often it has seen exactly that shape, and the seams land in strange places. Put a space before kaleidoscope and it splits as kale, eidos, cope. There's a kale hidden in kaleidoscope. Nobody put it there. The seams aren't logic. They're statistics, frozen into a dictionary. And the seams don't stop at words. Numbers get chopped too. A long number doesn't split into the tens and hundreds columns you learned in school. It splits into chunks of digits, wherever the dictionary happens to cut. Two similar numbers can be carved in completely different ways. A strange foundation for arithmetic. Keep that in mind the next time a model slips on arithmetic. We'll come back to it late in the season. And a grown dictionary has weeds. In 2023, researchers found words in an older model's menu that shouldn't exist. One was a Reddit username, Solid Gold Magikarp. It showed up so often in the text used to build the dictionary, it earned its own block. But it was filtered out of the text the model actually learned from, a block with nothing behind it. Ask that model to repeat the word, and it kept answering, distribute, a word the machine can see but cannot say. Researchers call them glitch tokens. Newer menus were cleaned up, but a grown dictionary can always hide weeds. One more consequence. This one costs real money. The footpaths were worn in mostly by English text, so English gets big, smooth chunks. Many other languages get chopped into fragments. Researchers measured it in 2023. The same sentence can take several times more tokens in Burmese or Amharic than in English. And AI companies charge by the token. Same question, same service. A higher bill, and often worse answers. Nobody chose this either. That's what grown means. The blocks, the seams, the weeds, the bills. So what does it all add up to?
Step back and a lot of AI's weirdness clicks into place. Spelling troubles, rhymes that don't quite rhyme, arithmetic that slips on long numbers, different bills for different languages. All of it traces back to the front door. The machine never sees your letters, it sees the blocks. None of it is malice, and none of it is stupidity. It's just the shape of the front door. Two things to try. Ask a fast model how many Ks are in Bookkeeper. Not Strawberry, that one's been memorized. Bookkeeper is a lovely case. The tokenizer cuts it right through the double K. Book, then keeper. And search for a tokenizer playground. Paste your own sentence. You'll see the seams. But reading is the easy half. Once the blocks are in, the machine has to answer, and it builds that answer in a stranger way than you'd guess. Watch the words arrive next time. There's a reason they come one at a time. That's Chapter 2. That's the front door of the machine, lit. 8 rooms to go. This was Owlspect, Chapter 1 of How a Machine Learns to Talk. We make the invisible parts of AI visible.